I will go to explaining what the theory predicts for these higher order correlation functions and why they are interesting, what can we learn about the early universe from them. And finally, I will talk about current and future constraints and observations. This talk will be sort of an overview talk. I didn't want to focus too much on my own work. I wanted to give a sort of overview, but of course, this is a biased overview because, of course, I will talk about my own work as I go on. So, what is inflation? I won't bore you with telling with the usual story of the flat potential, blah blah blah. I just want to say that what we care most about from inflation is the fact that it gives us a dynamical mechanism to generate primordial fluctuations that we observe in the CMB and that seed the formation of galaxies and the large-scale structure of the universe. In particular, after much work, one can write down the action, the second-order action, for metric perturbations, and this looks like the action for a scalar field, as you usually have in field theory, with a few differences. First, there is this coefficient in front, which is just a normal. You can see it just as a normalization, but more importantly, you see that the space derivatives. So this field is massless with no potential. It looks like that because it's a description of the metric fluctuations. And most importantly, space and time derivatives are separated. They have different coefficients. And in particular, this is due to the metric. It's because it's not a Minkowski metric, but an expanding metric. And most importantly, this looks like the usual scalar field that you quantize as harmonic oscillator, like in standard quantum field theory, but it has a time-dependent frequency. Since it has a time-dependent frequency, this means that quanta are constantly being created. Because if you start in a vacuum state, as time goes on, this state will no longer be in the vacuum and you create quanta. And moreover, so we can quantize this scalar field and compute correlation functions, as you always do in field theory. So for example, one can compute the two-point correlation function, which is usually parameterized in this way. So it's proportional to the Dirac delta of momentum conservation. This is 3 momentum. Sorry, I forgot the arrows. This is 3 momentum. We do it at a fixed time. So it's proportional to the Dirac delta of momentum conservation. It has some amplitude that one wants to measure, and it goes like a power law. When this number, ns, is equal to 1, this power law is scale invariant. And we think that these correlation functions can be observed when they are generated. These correlation functions that are generated during inflation can be observed even if we don't know the physics between the end of inflation and, let's say, nucleosynthesis, because outside of the horizon, because of the way the scales evolve. So basically, if I take some scale in the problem, say 1 over k, the scale of some quantum, of some fluctuation, of some metric fluctuation, and I compare it with the comoving horizon, during inflation, the comoving horizon shrinks, the scale exits the horizon, and then it freezes. So whatever information was there was encoded during inflation is frozen and kept for later on. Then inflation ends, the comoving horizon starts growing again, and at some point in the future, say much after nucleosynthesis, but for example before the emission of the CMB, or even after the emission of the CMB, the scale re-enters the horizon and we can observe it. So we are directly observing what happened during inflation when this information was frozen outside of the horizon. So this is the basics about inflation. And we have learned a lot. Of course, the name of the game is to compare observations with some with theory. So we have observations and you can try to model them using Boltzmann codes like CAMB or CLASS, CMB fast, starting from some initial conditions that are generated during inflation. So you have some theory You compute these initial conditions, and then you evolve to compare two observations. And of course, in this way, you learn about the theory by using those observations. Now, and we have learned a lot from the two-point function. Now, these plots taken from Planck, from the latest papers, I think, I don't remember, have become famous. So this is the two-point correlation function of temperature. So these are basically temperature fluctuations on two different points of the sky correlated and transformed to a sort of Fourier decomposition on the sphere. So you transform them using spherical harmonics. And the predictions from theory that comes both from a scale invariant spectrum and then from the physics of the early plasma that is computed by these Boltzmann codes, the theory agrees very well with observations. And this theory has been used to put tight constraints on cosmological parameters. In particular, this plot is also famous. It has been used to put constraints on possible models of inflation. So we have learned a lot from the two-point correlation function. But there is more information. But this is only probing the free field. So it's only probing an action like this one. This action was obtained by expanding the metric and keeping it up to second order. Of course, there are higher order terms in the action that relate to the nonlinear evolution of gravity, but also to the interactions of the inflaton, etc., that we cannot see directly from this two-point function. So we would like to go to higher order correlation functions. This is similar to what you do in particle physics, of course, because in particle physics you do scatterings to probe interactions, and these scatterings are proportional to higher order correlation functions. So this is not very different. And I'm going to focus on the three-point function because in principle it's the easiest to observe. Each one of these zetas, which are metric fluctuations, has been observed to be to the order of 10 to the minus 5. So every time I include an additional zeta, is 10 to the minus 5 times smaller than the previous one. So I don't want to pay too many zetas, so I stop at the three-point correlation function. But in the literature also, four-point correlation functions have been studied and constrained, etc. It's also very interesting. But I'll limit myself to this. And this is proportional to a Dirac delta of momentum conservation, which basically means that the three momenta, K1, K2, K3, form a closed triangle. And whatever is left is what we usually call the bispectrum. So if you ever have heard a cosmologist talk about the bispectrum, he's talking about this three-point correlation function. Now, if this bispectrum is scale invariant, I can factorize one of the scales, say K1, and everything can be described in terms of the ratios, K3 with respect to K1 or K2 with respect to K1. And also, this should be invariant under the exchange of any pairs of 1, 2, and 3. So all the information is contained in this triangle in the plane. And people talk about, I'm going to talk about different limits in this plane that correspond to different configurations of this closed triangle that the momenta form. I'm going to focus a lot on the squeeze limit. It's going to be almost my main point during the talk. And the squeeze limit has nothing to do with quantum mechanics, with squeeze states or so on. It's only the limit in which one of the momenta is much smaller than the other two. So the triangle looks kind of squeezed. And it looks like this, and in this plane, it belongs to this region. Another configuration that we're going to talk about, that people talk about, is the equilateral configuration, where the three momenta are equal. So the triangle is equilateral. And also, some people talk about n-folded configurations, which looks like a flattened triangle. Okay, very good. So let me start by talking about the squeeze limit. The squeeze limit is very interesting. So I'm going to tell you why, from theory, these things are interested and what we expect in the different configurations. So the squeeze limit is very interesting because it encodes the relation between a very long wavelength mode, meaning very small momentum, meaning a very squeezed triangle, with short wavelength physics. And intuitively, this limit is kind of trivial, should be kind of trivial in many theories. And the reason is because the metric fluctuations are basically the gravitational potential. And we know that the gravitational potential, we have this Newtonian intuition that the value of the gravitational potential has no physical meaning. If I give you some value of the gravitational potential, you can change this value however you want. You can raise or lower the value, and it should have no effect on your short scale physics. So if I approximate this long wavelength mode as a constant, because it's very long wavelength, then basically it should have no physical effect. For example, if I have a very nonlinear object like a galaxy, which are super complicated, and I rescale the Newtonian potential, nothing should happen to this galaxy. And the same happens to the gradient of the potential, because a gradient of the gravitational potential is just a constant gravitational force, so we should also be able to describe it. Actually, we can do this. So this is Newtonian intuition. We can do this even in GR. To see it, let me start from some unperturbed Friedman-Robertson-Walker metric, which looks like this. And now I do a coordinate change. So I change time and space in this way. And now the metric looks like this. So it looks like a perturbed metric. And indeed, if I set this to 0 and set this to zeta, to be equal to zeta, it looks like a perturbed metric of exactly the type that is generated during inflation. However, notice that this lambda is a constant, this epsilon depends only on time, such that this zeta is constant in space. So this only holds for a very long wavelength mode. And you can do the same for a gradient. And indeed, for inflation out of the horizon, epsilon should be 0, lambda should equal zeta. And what we learn is that a very long wavelength metric fluctuation is just a change of coordinates. So as in the Newtonian intuition, it has no physical meaning. This was already noticed by many people, Maldacena and also Weinberg. One can generalize this also to the gradient, following this Newtonian intuition. And we learn that there is no correlation between a very long wavelength constant mode and short wavelength physics. Now, what does this mean for the physics of inflation? It means the following. If I take the spectrum, so this is a symmetry of the theory, if you want. This is symmetry under diffeomorphisms. And it's spontaneously broken in the sense that the metric does not transform linearly. So one can see this the presence of this nonlinear symmetry as inducing some Ward identities that tell you how the 3-point function behaves in a soft limit. This is a more particle physicsy way of putting it. Now, so we learn from all this that the squeeze limit contains a lot of information. From the Ward identity or from these arguments that I gave you, then we know that the 3-point function in a soft limit, meaning when one momentum is going to 0, should have a specific behavior with momentum. So it should go like 1 over q. It turns out that all these arguments that I gave you are only true if this zeta, or this gravitational potential, is constant in time. And this is only true strictly in single field inflation. So if I have a single field inflation model, I don't care about which Lagrangian, which potential you gave the single field, which crazy theory you are looking at, as long as it's a single field inflation model, excluding some pathological examples such as ultra slow roll inflation. If I have a single inflaton field, meaning a single light degree of freedom active during inflation, which with energy much smaller than the energy scale of inflation, which is given by h, then the wave spectrum should go in this way. From explicit calculations that people have done, we know that if you have more than one field, the divergence in the squeeze limit is much stronger. So if we manage to measure this divergence, we will know what is the field spectrum of inflation. We will know how many fields were active during inflation. And if these fields have some intermediate mass close to the mass scale of inflation, you can even get some intermediate behaviors. I stole this figure from this paper here. Moreover, people have also started looking at a bunch of people, as you can see from this list, and this list is already old and more people should be added, have also started looking at what happens in the presence of fields with non-zero spin. What happens if fields with non-zero spin are active during inflation? These fields can induce a three-point function in this way. So this should be taken as a heuristic diagram. It's only saying that the interaction between two scalar fluctuations in this higher spin field, by higher spin I mean higher than zero, can induce a correlation, where I put one leg on the background, can induce a three-point correlation function. And it was shown first in this paper of 2015 and then later in others, that generically, in any of these theories, when you have when you exchange non-zero spin field, you always get this kind of this characteristic angular dependence, where the angle is the angle between the short mode, the k, and q, is the angle between k and q. So you get a characteristic angular dependence in this three-point function. So you can learn a lot about whether inflation was single or multi-field, and whether there was a light higher spin field, higher than zero spin field present during inflation by looking at the squeeze limit. So it's very interesting. But even if we restrict ourselves to single field inflation, meaning that in the squeeze limit there is basically nothing, there is still information in other configurations of the three-point function. In particular, one can, I forgot to put the citation here, but Cheung, Creminelli, Fitzpatrick, other people wrote a paper on some time ago in 2008 on understanding single field inflation as an effective field theory. So, as in any effective field theory, we first look at the symmetries. In this problem, the symmetries we don't have Lorentz invariance because we are on a curved background. So space and time are separated. So if I write the most general second order action, I should write for a massless field, which would be a sort of Goldstone boson that characterizes the difference between a constant inflaton hypersurface and a constant time hypersurface, but that doesn't matter for now. This pi is connected to zeta. There is a very simple relation. They are basically proportional. Then if I write the most general second order action, I can write spatial derivatives separate from time derivatives, and I put some arbitrary coefficient. So we learned that this field can propagate at a speed which is not that of light, even if it's massless, because it's coupling to the foliation of space-time. And up to here, we don't learn much. But let's go to higher orders. So if I go to higher orders, I would write down the most general cubic Lagrangian. So then I write down the most general cubic Lagrangian with one derivative per field. I stay to lowest order in derivatives because higher derivatives will be suppressed by some energy scale. And this is one derivative per field. And the two operators that I can write that separate space and time derivatives are these two. And if the breaking of Lorentz is explicit, the coefficients of these operators is general. But the foliation, the curved space-time, preserves local Lorentz. Only that it's spontaneously broken. I mean, there is in the universe, there is a preferred time, but this doesn't mean the Lorentz invariance is broken. It's only a spontaneous breaking. Your vacuum solution has an arrow of time. And you can see this by the fact that if you impose the spontaneous, you impose that Lorentz is still satisfied, albeit spontaneously broken, then these coefficients are not free. In particular, the coefficient of this term is fixed by the coefficient of the quadratic spatial derivative kinetic term, while this coefficient of pi dot cube is completely free. So we learned that we have two operators contain information on the spontaneous breaking of Lorentz invariance. Two operators that are, in principle are independent, and they generate configurations which are not squeezed. They tend to peak in other triangular configurations. They generate 3-point functions which are not squeezed. And there are some newer developments that I don't have time to talk about. For example, it would be very, if we are lucky and in the near future primordial gravitational waves are observed, one can try to start to constrain the squeeze limit of a gravitational wave with two scalar fluctuations. And it turns out that the squeeze limit is very much constrained. Even in multi-field inflation, it cannot be large. It can only be large if you break some very fundamental assumptions about inflation. So this the squeeze limit of this 3-point function basically tests some very fundamental assumptions about inflation. Things like whether isotropy, whether the early universe was isotropic or not, or even the symmetry breaking pattern during the early universe. A more recent and more famous result is what the authors like to call the cosmological bootstrap. It turns out that they showed that in single field inflation, the de Sitter isometries fix the shape of the 3-point function, and they managed to recover the simplest 3-point functions. It's still unclear whether one will be able to apply this to more complicated models, but it's an interesting connection between this the field of computing amplitudes, etc., from symmetries and cosmology. And also, people are starting to look at going beyond correlation functions. So looking at the higher order correlation functions, not directly by themselves, but looking at things like all possible cumulants in the probability distribution function, etc. And I put only one reference just to publicize work that people did in Chile by Gonzalo Palma, Bruno Schelling, Xingjiang Cheng, and Spiro Sipsas. So I think these are interesting newer developments. Now, that's the size of the theory. Of course, it's a biased view of what the theory tells us. Now, how can it be observed? The most direct way of observing it is by looking directly at the 3-point correlation function of temperature fluctuations in the CMB. And this has already been done by Planck. Another way of doing it is by looking at the large-scale structure. This is a picture of the galaxy distribution in the universe as measured by the Sloan Digital Sky Survey. And so we can define a galaxy number over density, meaning the number of galaxies in some region minus the average number of galaxies normalized. And we expect that galaxies form close to where dark matter is more concentrated, because dark matter dominates the gravitational potential, and we expect matter to fall in this gravitational potential. And the dark matter we expect to follow the metric fluctuations that were generated during inflation. Of course, they evolve very nonlinearly. So we expect dark matter to follow the gravitational potential that is the metric fluctuations generated during inflation. And so we could look at, for example, the 3-point function of this galaxy number over density. But as I will tell you, also in the 2-point function of this galaxy number density, there is information on non-Gaussianity. So let's start by looking at the CMB. First, let's consider a phenomenological model as an illustration. So imagine that I give you a field, metric fluctuation theta, which is some Gaussian metric fluctuation, meaning that it has 0 3-point functions, and I add a quadratic term. If I do this, I generate a 3-point function, sorry, this should be B, that looks like this. I generate a 3-point function that looks like this, and here I plot it in this triangle that I was showing you a while ago. This thing peaks in the squeeze limit, and this has a shape similar to that would be generated by multi-field inflation. Now, however, this is a purely phenomenological model. So what do I mean when I say that it has a shape similar to the one generated by multi-field inflation? People define an overlap between shapes as a sort of cosine in this way. And two shapes are similar if they overlap. And it turns out that until very recently, data could only be analyzed for very simple shapes that are so-called factorizable shapes, because a general bispectrum was prohibitively expensive for CMB analysis. Recently, people have developed new techniques to look at oscillations and more general shapes. But these simple shapes, the simple phenomenological templates, are still being quoted. So the one I'm showing here is the so-called local template. And again, it is similar to the one produced by multi-field models. It has a very strong divergence in the squeeze limit. And remember that single field should not have this divergence. So if we observe something like this, if we analyze the data with this shape, we observe a number which is high, we know that single field inflation is ruled out. But people have created more general shapes. So remember that in the EFT of inflation, there are 2 free operators. And people, so therefore, one could in principle constrain this kind of non-Gaussianities by constructing 2 independent shapes. People indeed have constructed the so-called equilateral shape, which is a bit of a misnomer. Of course, it's a non-zero 3-point function all over the parameter space, but it peaks in the equilateral configuration. And an orthogonal shape, which is orthogonal in the sense that it has nearly 0 overlap with the equilateral, such that you have 2 independent data points that you can compare with your single field model. And Planck has put constraints on this. I'm quoting the recent 2019 constraints to 68% confidence level. So the ones generated by single field inflation in equilateral or orthogonal configurations are compatible with 0, but the constraints are not very good. So if FNL equilateral of order 100 is still easily accepted, while the one generated by multi-field, the local shape, is much better constrained due to this strong divergence. It's much easier to see in the data. It's also compatible with 0, and the constraints are starting to become order 1, though I would say, since this is just 68% confidence level, I would say that they are more order 10. Okay. So what do we learn from these constraints by Planck? First, so remember, the local shape, the one of multi-field, is of order 10. First, we learned that everything is consistent with single field inflation. Single field inflation predicts a very small value for this divergence. It's 0, but there are some projection effects that generate a non-zero value, which, however, is very small. So single field inflation predicts FNL local to be of order 0.1 and fixed by the 2-point function. So its amplitude is not free. It should be related to the 2-point function that Planck already measures, this power spectrum of Planck that it already measures. So we are still a couple of orders of magnitude from achieving this precision, but since it's it's perfectly compatible with the data. So it's consistent with single field inflation. What does multi-field say? So the natural values for the local FNL in multi-field are order 1 if the non-Gaussianity is generated by some spectator field that is independent of the inflaton and decays into curvature contributes to a curvature fluctuation after it decays after inflation. So then FNL is predicted to be of order 1. We are only one order of magnitude away from order 1. And if it is very coupled to the inflaton, if the additional fields are very coupled to the inflaton, it's predicted to be of order 0.1, but free, not fixed by the 2-point function. And we are still far from observing this. What about the other shapes? So the other shapes, the equilateral, the orthogonal, etc. From this, we learned that the theory is consistent with a weakly coupled inflaton, meaning such that these cubic operators are not very large. Indeed, from the EFT of inflation, we learned that FNL equilateral, but also orthogonal, should go like h over lambda squared, where lambda is the scale suppressing these higher order operators. And current constraints imply that lambda should be bigger than order 10 times h. So inflation is consistent with being weakly coupled. So that's what we learned from the CMB. And one would hope that in the future we can improve on this. And the future lies in the large-scale structure. In future, I'm showing pictures of near future surveys, the Euclid survey done by the Europeans, LSST, which will take place in Chile. It's basically an American survey. And this one I forgot. I think this is DESI or DES. I think, I don't know. And fine, the large scale structure is the future, but it has a problem. It's an uglier observable because the CMB is linear. You can run a CAMB or class or any Boltzmann code to perturbative order and get good results for the CMB. But the large scale structure is intrinsically nonlinear, so it's much uglier. So it's like the difference between colliding leptons or colliding hadrons. Large scale structure will be like hadrons because it's very, very nonlinear, and perturbation theory breaks down, etc. So to see it, let me write down some simplistic model of large scale structure, where I write the dark matter density as a fluid that satisfies the continuity and the Euler equations. And we see that these equations contain nonlinear terms, as we all know from hydrodynamics. Hydrodynamics is very nonlinear. So we have to expand. So while we can be perturbative, one can expand this in a perturbative series. But not only that, this is just dark matter. What we observe is galaxies. And we expect galaxies to trace the overdensity of dark matter. However, and this connection between the number overdensity of galaxies and dark matter is called biasing. But this biasing can be nonlinear with some free coefficients. It can depend on K and many other complications. So all these nonlinearities generate a non-Gaussian signal, which is difficult to quantify, but doable. People are working on it. We are working on it. So what are the observables of the large-scale structure? One can observe directly the 3-point function. That's kind of trivial, but even the 2-point function contains some information. So as I said, bias is the connection between galaxies and matter. And let me consider the local model again. So where I have a gravitational potential and I add a quadratic term. This quadratic term correlates short wavelength fluctuations with long wavelength fluctuations. So imagine a very simplistic model for galaxy formation. Imagine that I have some fluctuation that looks like this. It's a short wavelength fluctuation superimposed on a long wavelength fluctuation. And imagine that whenever the dark matter density becomes higher than a certain value, I form a galactic halo, a very simplistic model for galaxy formation. So in this picture, I will have a halo here and a halo here. This is for FNL equals 0. Both the short wavelength scales and long wavelength scales are independent. If it is positive, the short wavelength scales will be enhanced whenever I'm on a hill and suppressed whenever I'm on a valley. And therefore, I would form more galaxies. With the opposite sign, the opposite happens. So there is a correlation. So with FNL different from 0, there is a correlation between the number of galaxies and the gravitational potential. And this correlation goes like 1 over k squared, simply due to the Poisson equation, because density is Laplacian times gravitational potential. This is the Poisson equation. Therefore, the galaxy number over density is connected, the galaxy number over density 2-point function is connected to the dark matter 2-point function, and therefore to the primordial 2-point function with a 1 over k squared dependence if we have a local non-Gaussianity. And moreover, this is sensitive to the squeeze limit because it's precisely the coupling between a long wavelength mode and short wavelength mode. So people are already using this to obtain constraints on local FNL, which are starting to be competitive with the ones of Planck. And there are, apart from nonlinearities, just to finish, there is an additional complication, which is the fact that one has to take into account general relativity when you compute this. Relativistic effects are very small in the large-scale structure because most of the large-scale structure, most of the things that we're interested in are deep inside the horizon, deep inside the Hubble radius. Therefore, relativity is basically negligible. But non-Gaussianity is also a very small effect. And they turn out to be of the same order of magnitude. So if we care about non-Gaussianity, we have to care about relativistic effects. And these relativistic effects, just to give you an example of some relativistic effects, we observe the number density of galaxies at some redshift in some position of this, in some direction of the sky. This is what we actually observe. And we separate this into an average plus this over density. And this average is simply this average density of galaxies is the number of galaxies, the average number of galaxies at some redshift divided by the volume of that redshift shell. However, for example, the frequency of the photon is sensitive to the gravitational potential. So the redshift will change with the gravitational potential. So I will induce in this way a correlation between the gravitational potential and the number of galaxies, which induces non-Gaussianity. People, I wanted to give you more examples, but I don't want to bore you. People have computed this for the 2-point function, trying to observe this scale-dependent bias that I told you about, and they see that indeed, if you care about constraining FNL to order 1, which is what you would like to learn whether there were several fields during inflation or not, this is degenerate with these relativistic effects. We have also computed it for the squeeze limit of the 3-point function, and some preliminary results also show that the relativistic effects, which are this red line and this orange line, are degenerate with a primordial signal, which is this purple line. However, we are still optimistic, and so we expect that near future observations, like the ones I showed, or the recently approved spherex, will be able to constrain FNL, at least the local one, to order 1. And from that, we will be able to learn whether primordial fluctuations were generated by a spectator field or not. And we may even look for higher spin fields. And if we are really optimistic, as observations improve, one can hope to go even further. So to conclude, to summarize, non-Gaussianity is sensitive to a field spectrum during inflation. It can be measured in the CMB or LSS. Measurements are underway. Current constraints are still far from the physically interesting region, but future surveys promise to start exploring that region. And finally, well, just because it's the thing I'm working on recently, GR effects are important if we hope to achieve a precision of FNL of order 1. So that's the end. Thanks for listening.
Thank you, Jorge, for the talk. It was very interesting, your seminar. So before going to the question from the audience here in the Zoom session, let me remind to the people that as you can see, now we are not using Hangout on Air. Now we are changing to the Zoom system. Thanks to the University of Illinois in this case. And we want to also ask to the people that are following us in YouTube to subscribe to the channel, also to our Facebook page, as well as to start to write your questions in the YouTube chat. So maybe we can start with some questions from the people here in the audience in Zoom, or the other presenters, I mean, all the other participants. So, okay. So Jorge, I have a question. In the beginning, when you were talking about inflation, so on, is it possible to include information or future information coming from the sector of gravitational waves? Because there are these stochastics that could lead some relation with inflation
Okay,
at some point.
so I'll answer at 2 levels. First, there is ongoing effort to look for gravitational waves produced during inflation in the polarization of the CMB. So this would directly look at gravity waves produced during inflation. I've seen some claims that they will be able to observe something like that during LISA, but they are optimistic to say the least. So I don't think that this future experiments will be able to see gravity waves, these gravitational waves experiments will be able to see gravity waves produced during inflation, unless you do something strange with your model. Well, something, let's not call it strange, let's call it extreme, unless you do something extreme with your model. So yeah, so this has nothing to do with, so I'm talking about the gravity waves produced during inflation. This has nothing to do with the stochastic background of gravitational waves that may be generated during a phase transition in the early universe, etc. So I was mostly talking about fluctuations generated during inflation.
Right. So, but in the because what about in the do you expect to have some kind of super optimistic scenario in case of cosmologies or inflation in the case of modified gravity, so on theory? You because some
You
models
mean,
of modified gravity can mimic some aspect of inflation, no?
yes, but in especially during inflation, the difference between modified gravity and not modified gravity is a bit blurry, in the sense modified gravity will always add some additional degrees of freedom to your dynamics. So many of these models can be understood simply as adding additional degrees of freedom. In that sense, they are very similar to inflation. Now, many of them that do inflation, they are just doing inflation in the sense that the additional degrees of freedom are inflating the universe. So in that sense, there is very little difference. Now, there are alternatives to inflation. They are, in my opinion, they are not very appealing yet. Maybe someone will come out with an appealing alternative. I'm not saying that inflation is the truth, but the ones that exist in the literature are not very appealing. And they don't often involve modified gravity unless one is thinking about loop quantum gravity and those kind of things. So yes, I would bundle most of the models of modified gravity for inflation inside the same group as inflation models, because it's just some additional degrees of freedom. You can see them as just some additional degrees of freedom active during inflation. So many of the things that I talked about still hold in those models.
Yeah, I don't know. Okay, on YouTube we have some questions, but they were kind of not so relevant for the. There was some discussion about in the case of particle and duality. So I don't know if people in the audience has questions, or the people in YouTube that they can still write questions. But I wanted to ask you what about the case of because you were talking about the future measurements with this large scale survey to try to, and only exactly the part that you're passing now. So I'm wondering, because most of the problems that there are when people study, for instance, structure formation in the case of dark matter is if they include or not include baryons, because at the end, galaxies forms in the sector where baryons are, I mean, galaxies, the observed galaxies are in the sector where there are overdensities of baryons. But there are, in principle, some dark matter clumps that are kind of invisible from the point of view of the emitting light or so on. So in the sense, because when you were talking about the multi-field inflation, you have these waves that said that in the principle there is a correlation between the gravitational potential plus the amount of galaxies observed in that wave. So there is a kind of, is it possible to disentangle, for instance, the gravitational potential itself, or to include this?
Well, no. So in galaxy surveys, it's impossible to disentangle the gravitational potential from galaxy number over densities. I mean, you cannot see the gravitational potential directly, but the hope is that at least at large enough scales, which is anyway where most of these effects we are looking for these effects, all these unknown physics of the involving baryons making a mess when they form a galaxy, etc., can be encoded in bias coefficients, like the ones that appear here. So they can be encoded in a bias expansion. People have even written this in an effective theory framework, etc., trying to argue that this is enough. And so it seems to work well. I wanted to add something else. Yes, however, these bias coefficients are unknown. So you're adding new free parameters to the things you want to measure. They are unknown and they can generate a non-Gaussian signal. So when you have to marginalize over them because you have no independent way of measuring them. And when you marginalize over them, unless there is a method that maybe I'm missing, and when you marginalize over them, of course, you lose information on the non-Gaussian signal. However, these bias coefficients cannot affect the squeeze limit. These nonlinearities coming from baryon, the evolution of baryons, or the evolution of the large-scale structure, cannot affect a signal in the squeeze limit, which is the most interesting one. And the argument is basically this, that no matter how complicated your galaxy formation, this correlation with a gravitational potential can only be primordial. It cannot be induced by nonlinearities. Because the gravitational potential Newtonianly, you're basically blind to it. Yes. So no short scale process can induce it, because you have no way of generating some absolute value of the gravitational potential. You can only generate second derivatives of the gravitational potential.
Oh, good. So let me just check again in YouTube. So people from the audience, I don't know, maybe Alejandro has a question or not?
No, thank you, Jorge, for your talk. It was very nice.
Okay, that was not a question.
That was a compliment. Okay, so I don't know. I don't have more questions. I mean, I want to thank you, Jorge, because it's super interesting your talk. In fact, I mean, I am not from the exactly from the field. I mean, I'm not familiar so familiar with inflation, but I really enjoyed because I learned a lot about the how to observe this, what is are the observables that you're looking and what is the expected signature, and let's hope that it's going to be an optimistic future with this.
Mhm.
Okay, so thank you, Jorge, for all the rest of the people that are looking the webinar series. We are back. We are going to continue with the same schedule that we were having in the past, more or less each 2 weeks, 3 weeks. We're going to have a new webinar talking about different aspects of physics, astroparticle, cosmology, particle physics, so on, most of the fields of the science. So we are going to see again in the next webinar. So bye. Thank you, Jorge. Thank you, everybody, to participate.
Bye. Thank you for listening.